Section 4.7, difficult limits. What is a difficult limit? Here is the definition. When we compute a limit with a direct substitution, and we cannot get the answer, then the limit is a difficult limit. And the book calls the limit an indeterminate limit. Indeterminate here means cannot be determined by a direct substitution. When we compute a limit with a direct substitution, if we get one of the following, then we cannot determine the answer, and therefore the limit is an indeterminate limit. When we get 0 over 0, we cannot tell what is that. If it is 0 over 1 million, we are sure we can tell 0. If we get 1 million over 0, we also can determine it is infinity, but 0 over 0, any number can be possible. So we cannot determine what is 0 over 0. Similarly, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to 0, we cannot determine what they are. 0 to 0, 0 to 1 million, we can determine it is 0. 1 million to 0, we can say it is 1, but 0 to 0, we don't know what is that, okay? And also infinity to 0, 0 to infinity, 1 to infinity. We cannot tell what they are. In total, there are so many times of indeterminate limit. Okay, now today's topic 1, okay. Essentially, section 4.7 says that an indeterminate limit can be computed by derivatives. The following formula is called L'Hopital's rule. L'Hopital's rule use derivatives to compute an indeterminate limit. Suppose we have a quotient of two functions, and suppose we want to compute this limit with direct substitution. Directly plug in A in X. If we get 0 over 0 or infinity over infinity, then L'Hopital's rule says that we can compute this limit by this limit. This limit, take derivative on F, take derivative on G. Yeah, this formula is called L'Hopital's rule. About L'Hopital's rule, two things we need to pay attention, okay? One, L'Hopital's rule only handles indeterminate limits of type 0 over 0 and infinity over infinity. That means that L'Hopital's rule can only handle the first two times of indeterminate limits. If a limit is one of the following, the remaining times, then how to compute the indeterminate limit? In the case, you need to transform the limit into one of the first two times, then apply L'Hopital's rule. You cannot directly apply L'Hopital's rule to compute a limit of these times. Yeah, of these times, okay. So pay attention here. L'Hopital's rule can only handle the type 0 over 0 and infinity over infinity. Cannot handle the remaining types. Second things you need to pay attention is L'Hopital's rule here. Take derivative separately on the function f and g. Don't take derivative on the whole quotient. This is a common mistake. I often saw in the last several semesters, students compute this limit by taking derivative on the whole quotient. This is wrong, okay? Take derivative separately on function f and g. Yeah. Okay, now in the following, let me show you examples about how to use this formula, this equation, okay, to find indeterminate limits. Example 1, we have a quotient. We want to compute the limit as x approaches pi from the left-hand side, Yeah. Okay. Now, direct substitution. Okay. Plug in pi in x, then we get this. Calculator. Sine of pi is 0. Cosine of pi -1. So we get 0 over 2. Oh, 0 over 2. We can determine it is 0. So this limit is 0. Actually, this limit is an easy limit, not a difficult limit. Direct substitution can handle this limit. So for this limit, I put a warning. This limit is not an indeterminate limit. So you cannot apply L'Hopital's rule. L'Hopital's rule handles difficult limits. And also those difficult limits are either one of these two types. Okay. Okay, more examples in the following. Example 2. Find this limit. Try direct substitution first. Plug in 1/2 in x, then the limit is this number. But this number is 0 over 0. We cannot determine it. So we turn to use L'Hopital's rule. This is a difficult limit of the time 0 over 0. So we can apply L'Hopital's rule. Take derivative separately on the numerator and on the denominator. Then we get this limit. Now try direct substitution again. Plug in 1/2 in x. This time works. Direct substitution works this time. We get 11 over 20. So the limit is 11 over 20. Example 3. Find this limit. Again, direct substitution first. Plug in 1 in x, then we get this number. Calculator, lateral log of 1 is 0. Again, we obtain 0 over 0. We cannot determine the limit. But we can, because this is a difficult limit of the type 0 over 0, we can apply L'Hopital's rule, okay? By L'Hopital's rule, this limit is this limit. Take derivative on the numerator over derivative on the denominator. Lateral log derivative is 1 over x. X minus 1 derivative is 1. So then we get this limit. Now, how to find this limit? Directly plug in 1 in x, so we get the limit is 1. So this limit is 1. We can use a table to verify that the limit is 1. Yeah, we can use a table. Yeah, the limit indeed is 1. The function approaches 1. In the following 2 examples, we need to use L'Hopital's rules twice. Example number 4. Find this limit x approaches positive infinity. What number this quotient will approach? Directly plug in infinity in x, then we get infinity over infinity. That means as x approaches infinity, x squared minus 4 approaches infinity. 2x squared plus x minus 6 approaches infinity. So infinity over infinity. We cannot determine what is infinity over infinity, but we can apply L'Hopital's rule, right? Infinity over infinity. So by L'Hopital's rule, take derivative on numerator, take derivative on the denominator, then we get this. We get this limit. X approaches infinity. Denominator approaches infinity. And also numerator approaches infinity. So again, this limit is indeterminate limit of the type infinity over infinity. When you plug in infinity in x, we cannot tell what is that, okay? So this limit is a difficult limit of type infinity over infinity. So we can apply L'Hopital's rule to this limit. Take derivative on the numerator, take derivative on the denominator. Then we get 4 over 2. 4 over 2. Okay, now this limit is a constant. The function is a constant. So the limit is 2. Limit is 2. So this limit is 2. Actually, it is the leading coefficient of the numerator over the leading coefficient of the denominator. Yeah. So in this example, we apply L'Hopital's rule twice. Example number 5. This example, we also need to apply L'Hopital's rule twice. Direct substitution, plug in infinity in x, then we get this. E to infinity is infinity. Infinity squared is infinity. So we cannot tell what is this. Yeah. Yeah. As x approaches infinity, Ex approaches infinity. Yeah. As x approaches infinity, x squared also approaches infinity. So we get infinity over infinity. This is an indeterminate limit of type infinity over infinity. So we can apply L'Hopital's rule to compute this limit. Take derivative on the numerator, derivative on the denominator. Then we get Ex, derivative is Ex. X squared, derivative is 2x. Then how to tell this limit? Plug in infinity in x, then we get infinity over infinity again. So this limit is an indeterminate of type infinity over infinity. So we can apply L'Hopital's rule to this limit. Take derivative on the top, take derivative on the bottom. Then we get this limit. Okay, now as x approaches infinity, ex approaches infinity. Denominator is a constant, so the whole quotient will approach infinity. So therefore, this limit is infinity. Okay. This limit is infinity. That means that as x approaches infinity, e to x approaches infinity much faster than x squared approaches infinity. So the ratio approaches infinity. The top numerator approaches infinity exponentially. Denominator approaches infinity algebraically. So exponentially to infinity faster than algebraically to infinity. So the quotient is infinity. The answer is infinity. Yes, L'Hopital's rule is powerful in the computation of a difficult limit. But sometimes solution through L'Hopital's rule is tedious, as so in the following example. Example number 6. Evaluate this limit where x approaches positive infinity. Now solution 1. In solution 1, I want to use L'Hopital's rule to solve this problem. By direct substitution, I plug in infinity in x, then I get this limit is this number. But this number is infinity minus infinity. So I cannot tell what is the number. This is a difficult limit. Because the type is infinity minus infinity, it is not the type of 0 over 0 or infinity over infinity. So I cannot apply L'Hopital's rule to this limit. So I need to change this limit into a limit of either this time or this type. For the purpose, I make a change on variable. I let x be 1 over t. Okay. Now, plug in 1 over t in x, then we get this limit is this limit. 1 over t approaches infinity is equivalent to t approaches 0. And 1 over t minus 2 is this fraction. 1 over t minus 4 is this fraction. So this limit is equal to this limit. Now, basic algebra. Square root of a fraction is fraction of square root. Square root of a fraction is fraction of square roots. Basic algebra. Because these two terms, their denominators are equal, so I can combine these two terms to get this limit. Now, if you plug in 0 in t, then you will see that this limit is 0 over 0. This is an indeterminate limit. The type is 0 over 0. Now, I can apply L'Hopital's rule to this limit now. By L'Hopital's rule, this limit is equal to derivative on the numerator over derivative on the denominator. Okay, now derivative on square root of t is this. Derivative on the numerator. Compute derivative on the first term. we need to use chain rule. Derivative on the second term, also we need to use chain rule. Tedious. Okay, now simplify this function. We get this function. Now, direct substitution. Plug in 0 in t. Then we get the limit is 0. So, solution 1, I use L'Hopital's rule to solve the problem. Okay. Solution 2, I don't use L'Hopital's rule to solve the problem, but use algebraic conjugate. The solution by algebraic conjugate is much simpler than the solution by L'Hopital's rule. Okay, now I want to find this limit. This is a minus b. So a minus b, algebraic conjugate is a plus b. So multiply numerator by a plus b. At the same time, multiply the denominator 1. I can view this guy as a fraction. Multiply 1 by the same thing, a plus b. Okay. Now, numerator times numerator, a minus b times a plus b by formula is a squared minus b squared. Denominator 1 times denominator, so we get this. Now simplify the numerator. Square root, square, cancel. Square root, square, cancel. And then cancel 1x. Then we get numerator is 2. Okay, now this the limit about this function is easy to tell now. Okay, you can either plug in infinity in x to get 2 over infinity. The limit is 0, or by inspection. X approaches infinity. X minus 2 will approach infinity. X minus 4 will approach infinity. So square root of infinity plus square root of infinity is infinity. So, so 2 over this guy will approach 0. So this example, from this example, we see that in mathematics, low method is perfect. Even though L'Hopital's rule is powerful, but sometimes very tedious.